Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today I just want to recap on the previous problem we just did, published last week. I was thinking about it and I think there might be a better way to explain it. I think if we think in reverse, for some people it's going to be easier to understand what's going on. So let me just copy this house here that we use on the thumbnail. Let's just recap what's going on. We have the house that's losing, right? It's losing 55,000 kilojoules, and I don't have space. 55,000 kilojoules every hour, right? And we're saying that, if we want to keep this house at its cozy 25 degrees Celsius, then we need to put back the same amount of energy, right? The same 55 needs to go back in, so that we have equilibrium and this house does not cool down. Because if we don't, right, because there's a difference in temperature here, this energy that keeps leaving is going to make the inside of the house cool down. Brilliant. Now, let's think about this. If you recall, what the question was asking us is, part A, how long does the pump need to operate, the heat pump? How long the heat pump needs to operate? B was, what's the cost of operating this heat pump? And C was, what's the cost of operating this same, if we wanted to keep the house at the same temperature, but then using an electrical heater instead of an electric heat pump. Electrical heater. All right. So what I'm going to do now is we're going to, obviously the problem is the same, so the numbers are going to be the same, but we're going to flip the way we think about it. All right. First thing we're going to do is just start with the last piece of the puzzle, which is part C, and calculate what is going to be the cost of it. And this is pretty straightforward. If the cost of electricity is 11 cents per kilowatt hour, that's what we need, and we need to remove this much, we need to give this much energy, then that's the amount of energy we need in kilowatts. But this is not in kilowatts because this is an hour. So the first thing we're going to do, and we didn't do this on the last problem, we didn't do this, we did it, just kept it with that weird unit and convert it into per days. So let's start with doing that. So this is kilojoules per hour, and we know that for every 1 hour we have 3,600 seconds, right? So then 0, 0, 0, 0, 550 divided by 36, that will be approximately 15.28. And then in this case here, if 0.28, then this is kilojoules per second, right? Which is the same thing as a kilowatt, right? And then it's a unit that we're more used to dealing with. Okay, so if I need to put in 18.28 kilowatts, right, 18.28 kilojoules per second, then that means that I need to put in 15.28 kilowatts. And note how what would happen here is kilowatts and kilowatts, and then we're going to have the dollars per hour, but we don't want the dollars per hour. We don't know how much dollars per day. That's what the question asks. So we know that in 1 day we have 24 hours, right? So therefore hours go away and we're left with dollars per day, and that will be same values as before, obviously 40.33-ish, right? 0.3, I think we said, dollars per day. So same answer there, straightforward. Okay, but now what we're going to do is the following. Remember that the idea here is that we have a hot reservoir, which is at 25 Celsius of our house. We have our heat pump in here, or we don't do heat up in here, and then we have our 2 Celsius, which is a cold reservoir. And for us to be able to, instead of instead of having the energy going from hot to cold, if we want to reverse this, then we need to put some energy into our system, which is the work that this heat pump does, right? And then the same thing applies. The coefficient of performance is going to be the desired output divided by the required input. All those good things are the same, and the same thing is going to apply, blah, blah, blah. We go on. This is, we want this, let's just give some names here. What we want is to maximize QH. What we need to put in is work, and then we keep going, and then we end up with that idea that 1 over 1 minus T on the low end, T on the hot reservoir, because it's a Carnot heat pump. This is super important. I'm just going faster because we did this already, and then we come to the conclusion that the coefficient of performance of this guy here is 12.96, right? 12.96 approximately. Okay, so we did this before. No, this is the part that I want to reverse the logic thought here, because what we did then may appeal to some but may not appeal to others. So what we can do here is, and I think this might be more intuitive, is the following. What is the required energy, all right? What is required energy work that this guy needs to do is if it has a coefficient of performance of 12.96. Well, if this is the case here, right? If the coefficient of performance is just what I want, which is QH divided by what I need to put in, which is work in, right? And we can do these in the form of rate. Then the work that I need to put in is simply the amount of energy I need to remove divided by the coefficient of performance, right? And in this case, the amount of energy I need to remove is 15.28 kilowatts, right? 15.28 kilowatts. And then the coefficient of performance, as we just calculated, is 12.96. Okay, there's no unit here, so whatever comes out of this is going to be the same unit as the amount of energy I need to remove. And it turns out that the work we need is 1.18 kilowatts. Okay, and then this might be more intuitive to some, because what we end up analyzing is the following. I have a heat pump that operates at 4.8 kilowatts, but I need one that only operates at 1.18 kilowatts. Okay, so note that I have an overpowered heat pump. We can think it that way, right? We have an overpowered heat pump, and if that's the case, then it doesn't need to work all the time, right? Because note that from here to here, it's almost 4 times more, right? If this were to be 2, it would be exactly 4 times more, but it's a bit more than 4, okay? So what this is saying is that, for instance, obviously this is not the case if the house is the same temperature the whole year, 25, and the whole year is 2 degrees Celsius outside. It means that this heat pump will only have to work about 1/4 of the year, and it's going to be 1/4 of the hour, 1/4 of the minute, 1/4 of the day, right? In this case here, we're interested in the day. Okay, so if we had exactly the power that we needed, if we had exactly the 1.18, and I'm struggling because this is too thick. There you go. If we had exactly the 1.18 kilowatts, then this would just stay on 24/7, right? Just stay on, and there you go, problem solved. But we have one that's more powerful, so that means we don't need it to be on all the time. We need it to be on for how long? Well, we need it to be on for the 24 hours times the proportion between these two, right? Which is going to be, almost 4, like we said. If it were 4 exactly, then, it would be just a quarter of a day, quarter of a day, which is exactly 6 hours. Because it's a bit lower, it's going to be a bit less than 6 hours, right? So it's going to be, let's see, this is 1.18 over here, and we're dividing that by 4.8. No, both of them are kilowatts, so they go away. We're going to be left with the unit of hours, right? And this is 24 hours per day. So the amount of time this guy needs to be working on a day is 5 point, whatever we got before, right? 5.8966, so approximately 5.9. Approximately 5.9 hours per day, right? So just to be sure, this doesn't mean that, you can turn it on for 5.9 hours and then turn it off and it's going to all be good. What this actually means is that, it can turn on for a little bit and turns off, turns on for a little bit, turns off. And the total time during one day it's going to be on, it's going to be 5.9 hours, right? And it's going to keep the house at 25 degrees Celsius as long as obviously the condition of being 2 degrees Celsius outside is kept. Okay, so I think this is more intuitive. And then obviously, if we want to close it off with so this was part A. So it's part A. If we want to close it off with part B, which is like what's going to be the cost, then there's two ways of going about this, two ways that might be intuitive. First way is, okay, I have this device, and if I don't do anything, if I need to use electricity, then this is going to cost me $40 per day. But I have this guy actually has a coefficient of performance of 12. So if I divide this by 12 points, it wasn't 12, it was 12.996, right? 12.96, it's going to be 12.96 a benefit. So I'm going to have to pay 12.96 less, which ends up being the $3.11 that we had in a day, right? Or the other way, which this is the intuitive way, I guess. The way that's more straightforward in terms of numbers is, all right, beautiful. I have the cost of electricity of $11 per kilowatt hour. And then I am using a heat pump that operates at 4.8 kilowatts. So kilowatts and kilowatts number. And kilowatts go away. And then I have, this is how much dollars per about 40 cents per hour. But I don't want to know per hour, I want to know per day. So I have 24 hours in one day. So therefore, hours go away. I'm going to be left with dollars per day. And this turns out to be obviously the same number, $3.11 per day. Cool. So, same problem, slightly different approach. Obviously, the numbers have to be the same. It's engineering after all. But the way we approach it might be a bit different and might make more sense for some of you. So I hope this helps you out. If it did, please consider liking this video. And if you have any questions, as per usual, just leave them down below and we'll talk soon.